So, let us note down some easy consequences of the above lemma. So, I will write in the form of corollary. Every Noetherian A module is finitely generated. Remember, in the lemma we proved actually the equivalence. A module is Noetherian if and only if every submodule is finitely generated. In particular, the module itself is finitely generated. So, this is immediate from the above lemma, and also let us write one example. The Artinian modules need not be finitely generated. Artinian module need not be finitely generated. Once you have such an Artinian module, that cannot be Noetherian. So, above we found an Artinian module which is not Noetherian, and we had to give an argument why it is not Noetherian. But if you note the general fact, then you do not have to give any argument for that. Okay. So, which is the, for example, which is Artinian module and not finitely generated? There are many. In fact, there is a big theory behind it. I am not going to go into that. But if you look at this module, Q Z local, this is 2, Z bracket 2. This is not finitely generated. Not finitely generated Z module. I would say check this, it is not too difficult, and maybe you might need, so possible that you can also prove, also check that Q is not finitely generated Z module. That means you cannot find finitely many irrational numbers, so that their Z linear combination is the whole Q. Of course, this will, for this you may have to use I would say the fundamental theorem. Theorem of arithmetic. Fundamental theorem of arithmetic everybody does in the school, that is, every integer is a product of prime numbers. So, that is what we have to use to check that Q is not finitely generated. Actually, much more, even more you can prove, even more. Prove that Q is not Z algebra of finite type. That is, Q is not of this form, generated as an algebra by finitely many elements. That means this is the quotient of the polynomial ring in M variable. No? So, even Q is not like this. So, therefore, studying linear algebra over Q or algebraic geometry over Q is much more difficult task than studying it over real numbers or over complex numbers. I will show you complex numbers are the easiest to deal with. Alright, so now let us go back to our remember I said that I want to prove that every Noetherian ring is Artinian and structure theorem for the Artinian rings. So, this is what I want to deal, and for that I am collecting some basic results so that we can go on to more general setup. Alright, so still I want to give you more examples of Noetherian rings. So, let us recall what was the definition of Noetherian ring. So, let me recall here definition. A ring A is called Noetherian respectively Artinian if the A module A is Noetherian respectively Artinian. So, in particular from the above lemma and corollary, in particular a ring A is Noetherian if and only if every ideal in A is finitely generated. We do not have such a simple characterization of the Artinian rings. So, but anyway, if you prove Artinian rings are Noetherian, that we will prove it soon. So, now let us list what whichever rings we know they are Noetherian and which rings are not Noetherian. So examples. So, first fields are Noetherian. Because field has only two ideals, a 0 ideal and the whole ring, and both are finitely generated. 0 ideal is generated by 0 and whole field is generated by the unit element 1. So, therefore, all ideals are finitely generated, therefore, Noetherian. So, the second one, every PID, every principal ideal domain is Noetherian. In fact, the title this I will keep writing it as PID, where all ideals are principal here. In particular, they are finitely generated, in fact generated by one element, and therefore ring is Noetherian. And let us review how many PIDs we know. So, the basic examples of these PIDs are Z is a PID that we have already noted. If you take a polynomial ring over a field, arbitrary field in one variable, this is a PID, K is a field. One more PID is very interesting, that is you take the K arbitrary field and take the power series ring over K in one variable. This is the formal power series ring over a field K. The elements are the power series, and I would say even this ring is even better than the earlier two rings, because here I will just say the ideals in this ring so I will say here check that the set of all ideals in this ring is precisely not only principal ideals, but they are generated by the powers of X. So, they are generated by, so A is our this ring, X power R, where R varies in N. These are all ideals. So, in fact the ideals also have this ideal, this set is not only ordered set, it is also totally ordered. So, that is the advantage. And now we do not even know right now that if I take, for example, what about this ring? What about rings like this, Z polynomial in X or Z polynomial in many variables, Z x1 to xm, where m is at least 1, or a field K and polynomial ring in x1 to xm, where m is at least 2, or K power series in m variables, where m is at least 2. And K is a field. Are these rings Noetherian? I will prove the answer is yes, and we will need theorem of Hilbert. So, this we will in the future. Now, these are Noetherian. What about a ring which are not Noetherian? So, third, if I take now K field and polynomial ring in not finite variables, but countably many variables. Let us write it x1 to xn. So, I should use a short form xn, n in n. This is a polynomial ring in countably infinite many variables. This ring is not Noetherian. So, to justify this, I have to give an example of an ideal in this ring which is not finitely generated. For this, check that the ideal generated by xn, all variables, is not finitely generated. Because if it is generated by finitely many polynomials, each polynomial involves finitely many variables. So, finitely many polynomials will involve finitely many variables. So, if you pick up a variable which does not contain in a given finite set of polynomials, that can never be a linear combination of those polynomials, because I substitute the variables to be 0 which occurs in the polynomial, and the other side is the variable which is does not occur there. So, you will get a contradiction. So, therefore, that justifies, but I would say write formal proof for this. Alright. So, that have alright. So, next observation I will make now. So, this is again I will write it in a lemma form. So, this one says, so as usual our notation is let A be a ring and okay, let I would say let A be a Noetherian ring. Then every finite A module V is Noetherian. In particular, finitely generate subgroups of finitely generated abelian groups are finitely generated. So, just before I give a proof, I just want to clarify the term I have used here. Remember, I have used this term finite A module. So, note that does not mean the set is finite, but that means the module is finitely generated. When I say finite A module, this means finitely generated A module. Why did I make this convention or this notation? That is because remember when we say finite type A algebra, see algebra is also module. So, when I say finite type algebra, that means finitely generated algebra, finitely generated A algebra. That means not module, but as an algebra it is finitely generated, and this is as a module it is finitely generated. So, I do not want to use this finitely generated at all, because if you use for one and not for the other, then one might get confused, you are saying module or you are saying algebra and so on. So, for that the standard terms used in more serious algebraic geometry books are also finite modules and finite type A algebras. Alright, now the proof is very simple. So, proof. What do we want to prove? In particular part obviously follows, because every in particular subgroups of a finitely generated groups are finitely generated. See, finitely generated abelian groups are finitely generated Z module, and we have proved above that they are Noetherian modules, and therefore all subgroups which are submodules are also finitely generated. If you prove this, every finite module is Noetherian. So, start with a finite module. So, that means what? A finite module V looks like it is finitely generated. That means it looks like this. It is generated by finitely many elements A x1 to xm. That means this is a linear combinations of this given x1 to xm. And if I want to prove this is Noetherian, we want to prove this is Noetherian. To prove V is Noetherian, it is enough to prove that the cyclic A modules are Noetherian. That means we can assume m equal to 1, because if I prove each one of them is Noetherian, then remember one of the corollary says that the sum of Noetherian modules is Noetherian. Sum of Noetherian submodules is Noetherian. So, therefore, this will be Noetherian. So, enough to prove. But what is the advantage? But then we have a surjective map natural from A to AV. A to V. V is generated by one element, that is the meaning of it is cyclic module, and I have a natural map here, namely A going to AX. This is clearly surjective A module homomorphism. And we want to prove this is Noetherian. But you know, this is the image of this module A, and A is Noetherian ring. So, therefore, the A module A is Noetherian, therefore, V is Noetherian. So, that implies V is Noetherian A module, since the A module A is Noetherian. So, we have used all earlier observations one by one. So, now I will state few consequences again for this lemma. So, corollary 1, so let A be a subring of the ring B of B. So, A contained in B, this is a subring, means the same operations will make this A as a ring. Then if A is Noetherian, and if B is a finite A module. Remember, A is a subring of B, therefore, this B is an A module by restriction of scalars, and therefore, I can talk about whether B is a finite A module or finite type algebra. No, I am assuming now B is a finite A module, that means B as a modulo array generated by finitely many elements. So, this is B A y1 plus 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 A y m for some y1 to ym in B for some. That means B is a finite A module. If that happens, then B is also a Noetherian ring. Okay, let us prove this. All right. Because B is a finite module, by the above lemma, the A module B is Noetherian, because we have proved above finite modules or Noetherian rings are Noetherian. So, therefore, the submodules A submodules of B are finitely generated, because every submodule of a Noetherian module is finitely generated. So, therefore, every ideal in B, every ideal in B is also an A submodule, which is also A submodule of B is finitely generated. But then B is a Noetherian ring, because we have checked that every ideal is finitely generated. Therefore, B is Noetherian. Because we have proved above that the B module B is Noetherian if and only if every ideal in B is finitely generated, or if you like, you can also take ascending chain of ideals and check that they become stationary because they are finitely generated. So, therefore, that proves this. Okay. So, this also gives some more examples of Noetherian rings. Okay, corollary 2. Let A be a Noetherian ring and let B be a finite A algebra. What does that mean? That means first of all B is an algebra, and B is finite algebra means as an A module it is finitely generated. That is what I introduced the terminology. So, I will write first time, that is B is a algebra which is finite A module. As a module it is finitely generated, but it is an algebra. So, what is the difference between this and that? Here A is a subring. So, A may not be a subring of B in this case, but there is a ring homomorphism from A to B, that homomorphism may not be injective. So, that is the usual. So, in this case what is the conclusion? Then B is a Noetherian ring. Now, the way I have stated these corollaries, it will automatically give you what should be the next. The next is, now you might say, what did I said only about algebra which is finite, what about finite type algebras? So, the question I am asking is, let A be a Noetherian ring and B be a finite type algebra over A, and then can you say B is Noetherian? Of course, the answer is yes, and we will prove this in the next lecture. We will first prove Hilbert's celebrated theorem, which he proved in 1888, that is known as now Hilbert's basis theorem. I will also explain that time why he used the word basis, but beside that, this he proved for the application in invariant theory, and that was the first very fundamental theorem in commutative algebra, and you will see proof is very trivial, proof is conceptual and very trivial, and this also helped invariant theory people to prove their assertions about invariant theory. So, I will stop and we will continue in the next lecture. Thank you.